like it's recording, so we will get started. Couple of quick things we are fixing, because I'm always fixing to do something. We're fixing to do this particular problem, so while I'm going through the announcements and kind of stuff, you can be writing down the problem, because we're about to do this one. Just for everybody's information, I will be holding a problem work session in Tonkawa on Tuesdays at 12:30 in the physics lab, and on Fridays at 1:30 in the physics lab on the Enid campus. So I'll be working problems to help folks out. A couple of other things just to kind of think about. So far, really, even though you don't know it, so far we haven't covered anything that you didn't already cover in college algebra. I started flipping through the college algebra book the other day and went through and went, okay, all right. And then even it talks about, except for the fact that college algebra book does not actually use the word vector, which is a little bit of a disconcerting thing to me. But I was flipping through various parts of the book, and most of the stuff that we have covered has actually been mathematically discussed in college algebra. It's not until we get to projectile motion that we really have to introduce, other than the difference between displacement and total distance, the word vector. And what we're talking about right now in projectile motion, we really haven't covered something that you guys haven't seen before. It's just the fact that you walk into physics class, and it's the word physics that is putting you into a mindset that says, oh God, this is hard. And oh God, I've never seen this before. And I didn't get this somewhere else. You guys have been doing a lot of this since before you could talk. I know, because my granddaughter and my grandsons have severely tested me in terms of playing with physics. So it's something that you guys have done. It's by virtue of the fact that you're putting yourself into a mental mindset that says, A, this is hard, and B, I don't understand it. So now, everybody's heard the old saying, if you say you can't do something, you're absolutely right. Because you've put yourself into the mindset that you can't do it. And I want you guys to start switching your mindset into, I can do this. Because this isn't something that is intentionally difficult. Not until you get to some weird conditions does it become intentionally difficult. And that's where people start playing with and arguing about certain things, of which the science news as of last Friday is they actually measured the radius of a proton. And that's kind of an interesting thing because they're arguing about it. And physicists tend to argue about that kind of stuff. And I'm going, look, that's not a big issue for me because I deal with it once it's in an atom. So I'm not worried about it. So I'm not a higher energy physicist. So I really want you guys to start thinking about this not as something that's hard, because it's not. It's a new way of thinking about information that you already know. Okay? So think about that statement for a second. It's a new way of thinking about something that you already know. And that's one of the things that we kind of have to look at. And it's a problem solving. You know, so if you like puzzles, that's what these are. These problems are puzzles. And that's really what you're looking at. So I will do problem solving sessions on Tuesdays over here in Tonkawa and Fridays in Enid in the physics lab, because I know there's nobody in the physics labs. Okay. So other tidbit is there is a quiz out there on Blackboard. It is on kinematics, and it's due tomorrow evening, I believe, at 7 p.m. I just looked at it, and now I've forgotten. I'll look at it again.
That's at 11 p.m.
11? It's due at 11. Okay, yeah. So it's due at 11. You do get 2 chances to do it, and that will, and I take the highest score of the 2 chances. And I always do 2 chances because the internet sometimes is iffy and things don't always work out. So, other questions? And you guys over in Enid got to kind of have to flag me down if you've got a question. Same with you guys in here too. So, all right, so we got a roller coaster that moves 200 feet horizontally, and then it's going to go up a rise, and it's going to travel a distance of 135 feet at an angle of 30 degrees. Find the displacement. This is a vector problem, okay? So the first thing that you got to do, and this is one of the things when you guys get the test next Wednesday, if it's applicable, I give partial credit. It will be a multiple choice test, but if it's applicable, I give partial credit. And if it's applicable, when I'm saying applicable, for example, a question might read, a ball is falling, or a ball is dropped from a height. What's its acceleration? 32 feet per second, 9.8 meters per second, 9.8 meters per second squared, or 64 feet per second. Well, that one, there's really no partial credit. You got to know what the acceleration due to gravity is. And you'll notice that I used wrong units on certain things, so you got to be careful because units are important. So that particular problem, partial credit wouldn't necessarily be applicable. But a problem like this, partial credit would be applicable. So to get your first partial credit, draw your picture. So we got a roller coaster that's going to move 200 feet horizontally. Then it's going to go up a rise, and that rise is at 30 degrees, and it's going to travel 135 feet. So this is my first vector, this is my second vector, and that would be a problem that you probably would have seen in a college algebra book, except it wouldn't have given you the 30 degrees. It would have given you that you went west or east 200 feet, and then you went north 135 feet. But in this case, we've got that part there. So I'm going to actually do this part here. I'm going to break it up into its components. This is the x side, or the adjacent side. So this is going to be 135 cosine of my 30-degree angle. And if I plug that into the calculator, I'm going to get 116.9 feet. This side is the opposite side, so it's going to be 135 sine of the angle, and that's going to give me 77.4 feet. This is the displacement that I'm trying to find, or we can call that the resultant vector. Okay? So I could do this problem a couple of different ways, right? I could use my equation for finding the distance between 2 points, because I know this point is 0, 0. And I now know this point is 200 plus 116.9, so that's 316.9, and it's 77.4 for that point. So I could use my equation to do it that way. I could also write my vector this way, because now this is in the x direction. It's 200 plus 116.9, and there's my unit vector in the x direction. And then this is my unit vector in the y direction. Now I can do the magnitude, which we usually use the absolute value sign for the magnitude. This is going to be the square root of 3 116.9 squared plus 77.4 squared. And when I plug that into the calculator, I'm going to get 326 feet. Now, to properly describe this, I'm going to need to figure out that angle. And if I have it in this notation, this is just going to be the arc tangent of my y divided by my x. And that's going to end up giving me, when I plug it into the calculator, 13.3 degrees. And that's one thing about physics problems. There's usually more than one way to do it. I don't particularly care if you're more comfortable looking at taking the distance between 2 points. I'm fine with that. Now that I have that side, I can do it a number of different ways. I'm fine with that because there's more than one way to do the problem. Totally more than one way to do the problem. And there's nothing that says you have to do the problem in the order in which the WebAssign tells you to do it, unless it's one of those step-by-step guided solution problems. Then you got to kind of follow their steps. But there's nothing that says when we're doing some of these problems that you have to find them in the order that the problem is giving you. Sometimes it's easier to find the last answer and then do the other ones. So that it's, there's more than one way to do it, which complicates things. Because many of you say, well, if I only knew which equation to use, I could figure out the problem. Well, sometimes, it may not necessarily make sense to use the equation that I'm going to start with. It may make more sense for you to use a different equation. And when we get to some things down the road, there isn't a standard equation. You get to make your own equations. So that's one of the things that you get to kind of look at. So we got everybody comfortable with this one? You guys good over there in Enid? All right, because we're going to go back and we're going to start dealing with projectile motion. So, in our toolkit, so if I'm starting to prepare my cheat sheet, right, some things I know I want to have on my cheat sheet. I want to make sure I have all three of these equations, because this was in our one-dimensional motion. That right there is our three kinematics equations that we have. The other thing that I'm probably going to want to make sure I have on there is my sine of my angle, my cosine of my angle, my tangent of the angle, and I probably want to draw my triangle so I know exactly which angle I'm worried about. So that's something I probably would be including on my cheat sheet. Now remember, you can have anything that you want on one side of an 8.5 by 11 piece of paper, provided it's in your own handwriting. Okay? Now, this is where things get a little entertaining. So we know for projectile motion, it's going to travel as a parabola. Okay? It's going to travel as a parabola. And if I'm looking at my velocity vector associated with this parabola, it's going to have an x component and it's going to have a y component. And this x component and y component are independent. They're totally independent of each other. The motion that's going on in the x direction is independent of the motion that's going on in the y direction. And with that parabola is going to help us out because it gives us some symmetry, but then we're going to throw in some other pieces to it. So I can write my x component equations and I can write my y component equations. So if I do this, my x is going to be my initial velocity in the x direction. So using subscripts is going to help me out. Times time, plus my 1/2 my acceleration in the x direction times time squared.
Is that VOX?
V initial, so it's an O subscript x. So this is my initial velocity in the x direction. This is my acceleration in the x direction. Now, when I'm dealing with projectile motion and how we normally deal with this, there is no acceleration in the x direction. The only acceleration that I'm usually working with is my acceleration due to gravity. So that term goes away, and my x distance is going to be my initial velocity in the x direction times time. I don't have to mess with this at all, and that's going to give me my position at any point along this particular situation. So this will give us, when they ask you what the range of something is, that's going to help us get range. Well, so let's look at my other kinematics equations. My velocity in the x direction is going to be equal to my initial velocity in the x direction plus my acceleration in the x direction times time. There's no acceleration in the x direction. So that equation is not going to help me out a whole heck of a lot. Nor is this one. Because I have no acceleration in the x direction. I'm going to turn this light off because I think it's hard to see in here. That better? Except we still have the camera doing the weird thing. So my x component simplifies greatly. Totally simplifies greatly. Now, the y components are independent. Things aren't as simple in the y direction. So I get y is equal to my initial velocity in the y times time. And now I'm going to get minus 1/2 gravity t squared. Because my acceleration in the y direction is gravity. It's going down, and that negative sign is telling me it's going down. So I'm going to get that negative gravity that's coming into play. My v in the y direction at any time is going to be my initial vy minus gravity times time. And I get vy squared is equal to v naught y squared minus 2g, and this is going to be my change in y. And a lot of times we do that a little differently. We say that this is 2vy minus 2gh because we're looking at the height. So a lot of times we're going to put in that h for height instead of a change in y. And depending on what physics book you look at, depending on whether you're looking on Chegg, depending on whether you're looking at tutor.com, whether you're looking at a few other things, a lot of times they will give you some where they've solved for certain aspects, like the maximum height, or they've done that, they've actually gone ahead and manipulated the equations for them. I don't typically do that. Okay, I just don't typically do that because I can always get those equations by working with these 4 equations for projectile motion. And so I don't necessarily clutter up my cheat sheet with those because I can get to them without necessarily having to write them directly down. I'd rather save my space on my cheat sheet for maybe writing out an example problem. Like the problem that the person is tossing the ball from the top of the roof problem. So those are our equations that we work with. So let's actually work a problem here that we can get and then get our bonus points or get our partial credit points. So we're going to start with a problem. We're going to do a soccer ball because, you know, we got soccer folks around here. So we're going to do a soccer ball. And we've got a ball that's going to be kicked. Okay? The ball is going to be kicked such that I'm going to actually give you its velocity components. Okay? The ball is kicked such that it has an initial velocity in the x direction of 40 meters per second, and it has an initial velocity in the y direction of 20 meters per second. So I've actually, in this particular problem, given you its components. Sometimes what we'll do is we'll say that that vector will give you its magnitude and its angle, and you have to calculate those two components. So if I do this, if I give you a vector v, and I need to calculate those components, the vector v is going to be, and I'm going to get my vector in its x direction. That's going to be the magnitude of my vector v, cosine of my angle, and then I would have this sine of my angle. And we'll end up working a couple problems where we have to actually get those components. So I'm going to get partial credit for drawing my picture, and I'm going to get partial credit for figuring out my x and y velocity components. So we're going to kick this soccer ball, and it's going to ending up down here somewhere. We're going to make the assumption that we're on a reasonably horizontal surface. We want to find the magnitude of v and its direction. We want to find that. We want to find the distance traveled. And we want to find the maximum height. And we want to find the time of flight. Okay? So that's all the information we want to find, and all we're given, at least told anyway, all we're told is the velocity in the x direction and the velocity in the y direction. I do know something else. I have my acceleration due to gravity is going down. And we know what that number is. 9.8 meters per second squared. Now this is why I say you don't have to do it in the order that it's written. Okay? Don't have to do it in the order that it's written. So, easy thing to do, right, is find distance traveled. Because we know from right here, okay, we know from right there, I can write that equation right away. So my distance is going to be my initial velocity in the x direction times time. Oops, I don't know time of flight. Well, that's kind of a bummer. So that's one of the things I got to figure out. So I'm going to end up scratching my head. We also know something about right here. Right? We know at this point right at the top, the velocity in the y direction is going to be 0 meters per second. So I might want to go ahead and try to find the maximum height first. So that one, and in this point here, I know the velocity in the y direction, I know my acceleration, and I want to find my height. Those are my variables that I have. So if I go over here and look at my equations, I want to exclude time because I don't have time yet. I want to exclude time, so I can go in here and use this to find my height. So I'm going to do velocity in the y direction is going to equal the initial velocity in the y direction minus 2gh. This is 0, and this is at the top. So now I get the initial velocity squared is equal to 2gh. So all I did was move this to this side of the equation. Now I'm going to take the square root, or I'm going to go ahead and divide by 2g. Those cancel, and I just have h. So if I know that this is 20 meters per second squared divided by 2 times 9.8 meters per second squared, that's going to give me, when I plug it into the calculator, I'm going to get 20 squared divided by 2 times 9.8. It's going to give me 20.4, and let's do the units. I get meters squared, seconds squared, divided by meters, seconds squared. Second squareds cancel, one of the meters cancel, and I end up in meters. So my unit analysis tells me I rearranged my equations correctly. So now I've got the height already. I've got the height. So I can do something else. I can find the time of flight. Because if I know the height here, okay, and I know the height there, I can use my y component to help me out. So let's use that y component to help us out. Because I've got y is equal to my initial y times time minus 1/2 gravity times time squared. Well, if I'm doing the total flight, right? If I'm doing the total flight in this case, y at this point is equal to 0. So now I've got 0 is equal to my initial velocity in the y direction, which is 20 meters per second times time, minus 9.8 meters per second squared divided by 2 times time squared, where I have 0 is equal to 20t minus 4.9 t squared. Now I just do the quadratic equation, right? I just do the quadratic equation. Or I can do it a couple of other different ways, but I can do the quadratic equation. I can factor out a t. Okay, so I know y is at 0 when t is equal to 0, which we kind of knew that, right? Because that's where we start, right? So I want to worry about this part. So I get 20 minus 4.9, t has got to equal 0. I get 20 is equal to 4.9 t. I get 20 divided by 4.9. And we're going to do this, I'm going to write out the units. This is in meters per second divided by 4.9 meters per second squared. So I'm going to end up in seconds, which is a good thing. So I'm going to get 20 divided by 4.9. And that's going to give me 4.08 seconds. So the time of flight is 4.08 seconds. Or you could use the quadratic equation and got your two answers. So now we have the height was 20.4 meters. The time of flight was 4.08 seconds. I can find distance traveled now. Distance traveled is going to be my initial velocity in the x direction times time. which in this case is 40 meters per second, times my 4.08 seconds, which just tells me that it's going to be 163.3 feet, or meters, sorry. I'm in meters, 160.3 meters. And now we can do the last one. Okay, we can do the last one. And the last one is finding the velocity, the initial velocity in its x direction, or its initial velocity. And we're told that Vx is equal to 40 meters per second. Vy is equal to 20 meters per second. So now I get my vector is going to be 40 in the I direction plus 20 in the j direction. The magnitude is the square root of 40 squared plus 20 squared, which when I plug that into the calculator, gives me 44.7 meters per second. My angle is going to be the arctangent of my y over x. And that's going to give me 26.6 degrees. Okay, so let's do something practical. Okay, we're going to do something practical. Because every one of us has done this. And you guys back there over in Enid have done it too. For you guys over in Enid, the trash can is by the back door over there, right? So I want everybody over in Enid to look at the trash can by the back door. Everybody in Tocqueville, look at the trash can over here. Okay? So you see the trash can. All right? You got frustrated with working physics problems, so I want you to take a piece of paper and crumple it up. All right? I want you to get a ball. I'm serious. Take out a piece of paper and crumple it up. Huh? All right. Yeah, you know what I'm about to do, right? You guys have figured it out. All right. Now, you may want to time it a little differently so we don't have 20 balls headed towards the trash can at the same time. Because there's at least 20 of you over there, and there's at least 20 of you in here, so you may want to stagger it, but I want you all to try and hit the trash can with your ball. Okay? Come on. Come on, I want you to try it. Now, of course, we're going to have to pick them up after the case. Somebody hit it? Okay, I got some. Now, every one of you has just done the problem that we're about to do. Okay? Every one of you has just done the problem about to do. Now, that does not account for skill level, right? It does not account for skill level. It does not account for skill level. So, because some of us are better at it than others. But if I'm sitting at the free throw line and I have my basket right here And I'm gonna actually use feet because most of us have a better feel for a basketball court in terms of feet. Basket can be 10 feet off the ground, okay? And we can have our person standing at the free throw line, okay? My person's a little short, all right? It could be my grandson trying to hit the basket up there, or it could be Donnie's little boy. That kid's wicked, man. That kid can hit from, but he's probably been shooting baskets since he could stand up. So, that's kind of how it is. But if we say that, and our person's going to shoot the basket 4 feet off the ground, all right? And then we're going to start from 4 feet off the ground. And we're going to try and have our projectile hit the basket. Okay? And it turns out that this is probably a half-court shot, because I think that's 47 feet. So you basketball players, is that a half-court shot, 47 feet, about that? Because if I'm at the free throw line, it's what, it's about 8 feet from the basket? So that's half-court shot. Okay, that's half-court shot. So we're going to say, all right, actually, we're gonna actually try to figure this out here. That I want to know the velocity. I actually want to calculate the velocity that's needed to make the shot. Okay? I want to calculate the velocity that's needed to make the shot. So I've drawn my picture. Now, the first thing I can do is I don't have to worry, I don't have to work the problem just as I've drawn the picture. Okay? Just as I've drawn the picture, I can actually simplify my problem just a tad. Right? Because that's 4 feet. So, at this point, it's going to be 6 feet. And this is now at a 0 point, and I don't have to worry about the fact that I'm shooting at 4 feet off the ground. So I can actually simplify my problem just a tad. Now my velocity, I can have my initial velocity in the x direction is x, or velocity cosine of the angle, and my initial velocity in the y direction is the velocity sine of my angle. Okay? Now, I know that the distance is going to equal the velocity cosine of the angle times time. And I can plug in for distance because that's 47 feet. Okay? I can also do my change in y is equal to v sine theta times time minus 1/2 gravity times time squared. And my change in y is going to be 6 feet is equal to v sine theta times time minus, and gravity in this case is going down at 32 feet per second squared. So that's going to end up being 16 times time squared. So I've got some challenges here. What I'm going to do is I'm going to solve this one for time. So this is going to give me 47 feet divided by the velocity cosine of my angle is equal to time. And I'm going to plug that into this equation over here. So I'm going to get 6 is equal to my velocity sine of the angle, 47 velocity cosine of the angle, minus 16 47 velocity cosine of the angle squared. We'll clean this up a little bit. Those velocities cancel. Sine over cosine, if I look at sine of the angle is equal to y over the hypotenuse, and cosine of the angle is equal to x over the hypotenuse, and tangent of the angle is equal to y over x. If I do sine of the angle over cosine of the angle, that's going to give me y divided by h, x divided by h. H's cancel, I get y over x. This is actually equal to the tangent of the angle. So now I've got 6 is equal to 47 tangent of the angle minus 16 times 47 squared. So 47 squared is 2209 times 16 gives me 35344 divided by the velocity cosine of my angle. Squared. Oh, that's velocity squared and that's cosine squared, because those were inside there. Now, there are some trig identities that you can use to simplify this problem. I'm going to simplify it for the purposes of time to say that this goes off at a 50-degree angle. All right? So I'm going to simplify it by giving you the angle. You could actually go ahead and use your trig identities to solve for the angle. And there's also multiple angles because we know I can do a variety of different shots to get it into the basket. So I'm going to simplify it. Slide it back up. So I'm going to simplify it right now by giving you the angle for the sake of time. And so we're going to use 50 degrees. So I'm going to start up another page here. So I've got that this is 6 is equal to 47 times the tangent of 50 degrees minus 35344 divided by v squared cosine squared 50 degrees. So this is going to be 6, and if I plug that in the calculator, this gives me 56 here minus, I'm going to do the 35344 divided by, let's do cosine of 50. Let's see if it's going to do this right, squared. Not sure, let me do cosine of 50. I'm going to square it. I'm going to do this, divide 3. I'm going to do the inverse. Okay, I guess I did do it right. So it's 8, 5, 5, 4, 2 divided by velocity squared. So I'm going to clean this up. This is going to be minus 50, because if I take this to the other side, that's minus. And I'm adding 6, so I get minus 50 is equal to a negative 85542 divided by v squared. The minuses can go away. Yay, that's a good thing. So I get v squared is equal to 85542. And I get v squared is equal to 85542 divided by 50. This gives me 1711. So v is going to be the square root of that. And this has got to be 41.4 feet per second.
how you got the number
35,344 divided by the cosine of 50 squared. Well, and this is one of those places you have to be careful in your calculator, okay? Because, let me do this, 35344, and then I'm going to do the cosine of 50 squared. So you do the cosine of 50. Cosine of 50 is 0.6427. You got to square that. You got to square that, and that gives you 0.413. So this becomes 35344 divided by 0.413. And that gives you 85542. Now, if you don't enter it in, depending on how your calculator handles this, is where you may end up with a problem in your calculator. So sometimes it's better to go ahead and do it individually instead of trying to type it into your calculator all at once. Because depending on how you entered it into your calculator, you could have entered in squaring the whole thing and got a weird number. That's why I did it twice, just to make sure I entered it in the calculator correctly. Now, here's the fun part. You guys did that in your head, and we just put some numbers to it. Because you all threw towards a basket. You'll always do more physics in your head than you can ever write down. Always do more physics in your head than you can ever write down. Okay, let me do one that's a little more complicated. So I got a hill, okay? That's a hill. And at the top of my hill here, I have another little slope. And my skier is going to come off the top of my jump. All right? We're going to do a ski jump in this case. You can do the slide into the pool kind of thing. You can do a couple of different ones, but we're going to do a ski jump. And my skier is coming off with a speed of 25 meters per second, only in the X direction. So our skier is just coming off only in the X direction. That tells us something that we can write down on our, let's see if we can get this to stop doing this thing. Okay, that tells us something that we already know that my initial velocity in the Y direction is going to equal 0. We also have the fact that gravity is going to be 9.8 meters per second squared. Okay? We can kind of anticipate that in this case, I'm going to draw my picture, we're going to get our arc, and he's going to hit at some point down the hill. And the question is asking us, making the assumption that our hill is kind of the hypotenuse of a triangle, we want to know the distance that the jump made. So we're trying to find D. Okay? We're trying to find D. So I can actually draw some things into my picture to help me out. This is X, and that's the distance from the bottom, or the distance from the end of the jump horizontally to where I land. And Y is the actual vertical distance that I traveled. So I'm going to break this up into its two independent equations. So X, in this case, is going to be our distance that we're looking for times, and we're going to get an angle, and we're actually given this in the problem. I just didn't write it down yet. We're given that that angle is 35 degrees. Because most ski slopes, when we're doing a ski jump, tell us what that angle is. So that's going to be the distance there, cosine, because that angle there is this angle here. And if you want to go back in your algebra book to talk about that, that's a rule of parallel lines. Okay? My parallel lines, this angle and that angle are the same. So that's, the distance is the cosine of 35 degrees. This one here is going to be distance sine of 35 degrees. So my x is going to equal the initial velocity in the x direction times time. So this is going to be the distance cosine of 35 degrees is equal to 25 times time. That's my first independent equation. Okay, that's my first independent equation. My next one I'm going to look at is I'm going to look at my y is equal to my initial velocity in the y direction times time minus gravity over 2 times time squared. My y is minus sine 35 degrees is equal to minus 9.8 divided by 2 times time squared. That's my second independent equation. So I have two independent equations. I have two unknowns. Time is not known. Distance is not known. I have two variables, which means I have to have two independent equations in order to solve for it, which I've got. I don't really care about time in this case, so I'm going to solve one of these equations for time, this one, because it's easy to do, and then I'm going to plug it into that one. So let's do that. So I've got distance cosine 35 degrees divided by 25 is equal to time. And then I have distance sine of 35 degrees is equal to 9.8 divided by 2 times squared. I got rid of the negatives because negatives on both sides, so I got rid of it. So I've got that part. Now I'm going to go ahead and, so I've got, if I want to go ahead and play with this, I've got 2 times the distance sine of 35 degrees divided by 9.8 is equal to time squared, which is now equal to distance cosine 35 degrees divided by 25 squared. So now I gotta play with this a little bit. So I've got distance sine 35 degrees. If there's gonna be a 2, 9.8 is equal to distance squared cosine 35 degrees 25 squared. Now, your book tells you to go ahead and carry things through. At this point, it's pretty much easier to start dealing with a number instead of the other. So we can actually do that. First thing I'm going to do is I'm going to get rid of one of these distances because I can cancel one side out. So I'm going to do 2 times the sine of 35 degrees divided by 9.8. This gives me 0.117 is equal to D. And I'm going to do cosine 35 divided by 25. And I'm going to square it. And this is 0.00107. So I'm going to get 0.117 divided by 0.00107 is going to equal my distance. And it gives me 108.97, or it gives me 109, and I'm in meters. So 2 equations, 2 unknowns. And in this case, it's easier to solve and plug in. Okay? Now, just so that you guys can refresh the 2 major tricks that we have, 2 equations, 2 unknowns. So, because we're going to use this other one down the way. So I've got an x and a y. So I'm going to have a number ax is equal to by plus some constant c. And that's my first independent equation. Then I'm going to have dx is equal to by plus e. That's my second independent equation. I was going, did I not? I thought I did. It's okay. So I've got 2 independent equations. Now I can do the same thing that I just did. I can solve for x and plug x into the other equation. But in this case, that's a pain in the tushy. I got a simpler way of doing it. Okay? In this case, when I have an equation that looks like that, I've got a simpler way of doing it. One thing I'm going to do is I'm going to take the second equation, I'm going to multiply it by a minus 1. So this becomes minus d minus, and then I got a minus e. I'm going to use the mathematical trick of subtracting those 2 equations. So I'm going to get ax minus dx is equal to by minus by plus c minus e. Those 2 things go away, and I get ax minus dx is equal to c minus e. Factor out an x, I get x is a minus d is equal to c minus e, and I can solve for x, and it becomes c minus e divided by a minus d. So this is one way to do 2 equations, 2 unknowns, because provided I still have independent equations. And there are times that this is going to actually be the easier way to do it versus having ax is equal to 3, or I'm going to just do it by, and AX is equal to CY plus D. This case you solve for y becomes AX divided by B, plug it into that one and you get AX is equal to CAX B plus D, and then you solve for X. So that's the other way to do two equations, two unknowns. But I have to have as many independent equations as I have unknowns. And when we get to physics 2, we'll get some interesting algebra that we have to play with where I have 3 equations, 3 unknowns. But most of the time here, you're going to end up with 2 equations, 2 unknowns. You good? Guys good over there? Okay. We're going to complicate things just a little more. Okay. This time, we've got a rocket. All right? And our rocket is going to propel itself up. It's going to have an acceleration of 30 meters per second. And it's going to travel a distance, and this is going to be 57 degrees. Okay? It's going to be 57 degrees. And once it hits this point, it's going to go just as a projectile motion. We're no longer going to have an acceleration. And if I'm reading my notes right, the change in distance at this point is 450 meters. So that's 450 meters. And at this point, we're going to stop accelerating, and it's going to just travel off as a projectile. So it's going to end up doing that right there. So the first thing I kind of want to do is I kind of want to figure out this point. All right? I want to figure out that point. And in this case, it's going to be y at that point is going to be 450 sine of 57. And my x at this point is going to be 450 cosine of 57. And when I do that, this ends up being 377 meters. And this one ends up being 245 meters. I have to figure out what my velocity is here. Okay? I have to figure out what my velocity is there. So I'm going to have to do something. I'm going to have to look at this part of the problem as an independent problem. And that is linear motion. So I have that the change in distance is 450 meters. I have an acceleration is 30 meters per second. And the problem actually does tell us that this happens at time is equal to 3 seconds. Okay, this problem actually tells us that time is equal to 3 seconds. So I have time is equal to 3 seconds. That is just a linear kinematics problem. Okay? My linear kinematics problem, I can do it a couple of ways. Okay? I can do that my change in position is equal to my initial velocity times time plus 1/2 AT squared. We know that that's 450. We know that that's 3. We know that that is 30, I didn't write it down right, that's 30 meters per second squared. So the only thing we don't know is that initial velocity. So I can solve for it. So I get 450 is equal to 3 times the velocity I'm trying to find plus 15 3 squared. Everybody see where I got my 15? 1/2 A, 30 divided by 2. So I get 450 is equal to 3V plus 15 times 9. That's 135. So I get 450 minus 135 is equal to 3V. And this is equal to 315 is equal to 3V. V becomes 105 meters per second. Now you see why, one of the reasons why I can only possibly give a comprehensive exam in Physics 1. Because we will be building on this stuff as we go. So this part of the problem is coming from my previous chapter. This part of the problem comes from projectile motion. So depending on what we want to find out at this point, we now know what our initial velocity is. Our initial velocity is 105 meters per second. I can find its x and y components. Because its x component is going to be 105 meters per second cosine of 57 degrees. My y component is 105 meters per second sine of 57 degrees. This ends up being 52 or 57.2 meters per second. This one ends up being 80.1 meters per second. Get that down there so you can see it better. And then I can do the same types of problems that we've been doing. We can find the range downfield. We can find the maximum height. We can find, now the maximum height, okay? Remember, the trick on this one, the maximum height has to consider the fact that I was starting at 377 meters. So I find the maximum height of the projectile, and I'm probably going to have to add 377 meters. So that we can get that part of it. I am sure brains are full at this time. I am absolutely sure brains are full. So on Friday, I should have a better idea of exactly what will be on the test. We can do a couple more projectile motion problems. And look at it from that perspective.